Okay, 15.6 Ksp. Work number 1, they're going to be writing some equations and write the Ksp equilibrium expression. And then do calculation number 3, 4, and 5. Okay, on the worksheet. Now, the good news about what I'm going to go over here is we've already kind of gone over it in an earlier lesson. We went over this already, Ksp. So I think I could just go through and work some problems for you, and that will be about it. Okay, so the first thing I'll do, 15.6, it says, like you'll do in the worksheet, write the balance equation for the following and write the Ksp expressions for these that are listed on the paper. One says copper 1 bromide, dissociation. So copper 1 bromide, CuBr, if it dissociates, it'll be in water. We don't even write water above that, but it dissociates into Cu plus 1 and Br minus. Now, this will be, you write it as this starts as a solid, and that will be aqueous, and that will be aqueous. So in all the Ksp expressions, it's understood that that is in water. Okay, you don't have to put H2O above it. And don't add H2O here either in that. We don't ever do it on these. It's not really standard. Now, if I want to write the Ksp, remember what you do is you say, okay, I'm going to put in everything that is aqueous or everything gas. There's nothing gas here. There won't be any gases in Ksp. Well, if there's a gas, you leave it out, okay? Because the Ksp will only have molarities, aqueous, aqueous. Cu plus 1 and Br minus 1, and they're both 1, 1. So that's it. Number 2 is much better, and I should have done it first, but oh well. It says you have bismuth, bismuth sulfide, bismuth 3 sulfide. So that will give you 2Bi plus 3 S negative 2. Now remember, to get the charges, you ought to know that from long ago. Sulfur is always negative 2. 2 times 3 is 6. So 2 times 3 is 6. So 3 and 2 have to be the charges on top. Don't ever leave the charges there. If you have to write an equation like this, or a net ionic, this is a net ionic equation for the dissociation of these two chemicals. Don't ever write the charges, and don't leave them there in your final answer. You can put them there, then a lot of times they'll say now below, type it in or write in. Some of you might be doing your AP online. Okay, so anyway, that's how it works. So the Ksp for that one will be the bismuth ion squared concentration and the sulfide ion concentration, S negative 2, cubed. Bi, there it is. And now here's another one I had to throw in to be fun, I guess. NH42 PO4. All right, so it's like diammonium phosphate, sodium diammonium phosphate. Okay, but anyway, what's going to happen is, in water as it dissolves, you're going to get Na plus. That's interesting because ammonium and sodium are both soluble. So you get 2 NH4 plus, and you'll also get phosphate. Now, is there something I'm not thinking about here? Will they all the way dissolve? Yeah, this is how I would write it. Okay, I don't think you're gonna have to worry about one like this. By the way, these are all pretty soluble anyway. So this would be a high value. Okay, but you wouldn't have to worry about that. Now, if they gave you a different reaction, and say they put Na plus, and they kept it together, NH42PO4, like it bonds or something, well then you'd write it that way, however they show you. But I don't think they're going to ask you to predict that one out. That seems like it would all be, well, that's how it would be. That's the dissociation equation for it. Sodium diammonium phosphate, yes. Okay, now for the calculations. This is the big stuff. And I will warn you, that these can be some of the easier of all the equilibrium. They're easy, But because they're easy, a lot of times people make big mistakes because they take shortcuts. So let's be careful on that. And here we go. So I got one copper, 1 bromide, and bismuth sulfide, and copper iodate. Calculate the solubility. If I give you, calculate the constant, and then calculate the solubility. I give you the solubility. Okay. It looks good here. All right, so, all right, here we go. B. I'm trying to make sure that I have everything covered here. I'm going to try, hopefully, to have every possibility. Copper 1 bromide has a measured solubility of that number. Okay, so first I'm going to write down the equation, that number. This one, I really don't like it. You know what? Yeah, I'll do it, but I think C is a little harder. I like to do the harder one first, but oh well, we'll do it anyway. Okay, so I'm going to make an ice box. And what we do is, we're going to say that in the beginning of this, this is a solid, and it ends up a solid. You still have to have solid at the end. In any Ksp equilibrium between a solid on one side and aqueous on the other, you always have to have what's called a saturated solution. You must have saturated solution. For Ksp, you have to have it. If you don't, then you will not have an equilibrium. Now, in the saturated solution, there will be some solid remaining. And they'll say that a lot. There is solid remaining. That means, oh, it's equilibrium. There has to be a little bit. Remember, I think I told you this before. If you add salt to water, just table salt, okay, it dissolves. You stir it, dissolves. How can you make it saturated? You keep adding it until finally you got a little bit of salt in the bottom, and you realize no more salt. I can keep stirring it all day. That will not dissolve at this temperature. So at that point, you know you are saturated. Okay, that's true in all of these Ksps. There has to be a little bit of solid there. All right, so it says now as you get to equilibrium, of course, some of the solid will break off, minus x. Then these are 0. That will be plus x, plus x. These are an easy one, x and x. So it said here, so write the ice box, and it says, calculate the Ksp value if the solubility is measured to be 2.0, 10 to the negative 4 moles per liter. I should have done, for B, I should have done something a little bit different, but oh well. I'm going to change problem C to make it a little bit more relevant and better for you. Okay, so 2.0 10 to the negative 4 mole per liter. 2.0 times 10 to the negative 4 mole per liter. What does that mean? It's the solubility of copper 1 bromide. So here's what it means. 2.0 10 to the negative 4 moles of copper bromide, 1 bromide, will dissolve in every 1 liter of solution. That's the solubility of it. I'll show you one little bit with that in a moment, but what I'm going to do is, when they give you the solubility, they are giving you this. I know I told you a long time ago, this is the solubility. Do I have, oh boy, do I have another, well, the green one. Okay. This is always the solubility. X is the solubility minus X. That is how much breaks off, how many moles per liter of that break off and dissolve. That's the solubility. So, when they give you that, they're giving you X. If they're giving you X in this problem, then you know that's 2.0, 10 to the negative 4, and that's 2.0, 10 to the negative 4. So they ask you to find the Ksp value. I'm going to find that, but I want to show you, well, I'll find it first. Okay. Then I want to show you something else. Ksp, we already talked about, will be Cu plus 1 times Br minus 1. Concentration. And they're all 1 and 1. That's an easy one. So this is a very simple 2 times 10 to the negative 4 to the first power. And 2.0 times 10 to the negative 4 to the first power again. So it's what? Is it 4 times 10 to the negative 8? Yes, it is. 4.0 10 to the negative 8 is the Ksp. All right, not a very hard one to do. There's something else I want to show you about this, and that is, all right, 2.0, 10 to the negative 4 mole per liter. I'm going to ask you this probably on a test or quiz, and I didn't put it, so call this part B. All right, what is the solubility in gram per milliliter? What would it be in gram per milliliter? Or, oh, you know what? Yeah, we'll make it gram per milliliter. Okay, here's how you do it. If I have 2.0, 10 to the negative 4 moles of, look at the formula, CuBr dissolved in every 1 liter, well, let's go back to like last semester, and you're going to see kind of similar. Let's first, forget the liter, let's change mole into gram. Moles of CuBr, change to grams of CuBr, and 1 mole of CuBr add on the periodic chart. Copper is 63.55 and bromine is 79.90. 143.45. Let me double check again. Yeah, 143.45. Okay, 0.45. If I stop the problem right now, I'll have the solubility in gram per liter. But I said let's get it in gram per milliliter. So they can give you either way, gram per milliliter, or mole per liter. That's why I'm doing this. Gram per, oh, I'm sorry, not gram. Now I'm going to change liter to milliliter. Instead of having liter on the bottom, I want to have milliliter on the bottom. That means liter on the top, 1 in 1,000 there. So multiply those and divide by 1,000. 2 times 10 to the negative 4 times 143.54 divided by 1,000. And it's a very small number, 2.9 10 to the negative 5 grams of CuBr per milliliter. 2.9 times 10 to the negative 5 grams of CuBr per milliliter. Okay, so make sure you know how to find the solubility. Let me see. I want to do some other things here, but let me just see how my time is going. You may have seen the past videos and thinking, he's wearing the same clothes. That's because, yeah, I'm trying to catch up a lot of stuff and wrap up a whole lot of things in this chapter. Let me see. Yeah, I could probably do one more at least. All right. This one, bismuth sulfide. Let me do a little bit of changing real quick right here. Bismuth 208.98. Wow. That's the mass of bismuth. $514.14. Could that be it? Okay. Yeah, 514.14. Okay, so okay. 0.103 grams of Bi2S3 will dissolve, a maximum, will dissolve in 1 liter to make a saturated solution. I am changing question number letter C to this. 0.103 grams of bismuth sulfide will dissolve in a 1 liter solution, with water, whatever. Not 1 liter of water, but about 1 liter of water, to make a saturated solution. Okay, they could do this. They could say this many grams in 1 liter, or this many grams in 2 liters, just like you're doing molarity and all that. So now what they're going to say is calculate the Ksp for bismuth sulfide. So, here we go. Bi2S3 is going to give you Bi plus 3, 2Bi plus 3, and 3S negative 2. So, we'll do our little icebox. But now, do we know, in a saturated solution, they're telling you the solubility right here. But you got to figure that out. So that's why I was playing with the numbers here. So what I'm going to do is I'm going to first say 0.103 grams Bi2S3. I've got to find out what is it going to be in mole per liter. Gram per 1 liter, what is that mole per liter? So grams, that's the molar mass. Oh, no, that's not the molar mass. Oh, no, I got to find the molar. Yeah, that was only bismuth. So I got to go from gram to mole. Okay, 1 mole is, and I erased it right there, 208 point, I know it was 514, but oh well, 208.98 bismuth times 2 plus, and sulfur is 32.06. So 32.06 times 3, and it's 514.14 grams of bismuth sulfide. That's the molar mass. Okay, now that would give me moles, and moles divided by liter would give me the mole per liter. Now they could have made it per milliliter, and I was going to do like I did a moment ago on the problem, but I'll make it a little bit more simple. So that's how many moles you have. So 0.103 divided by 514.44 is 2.00 10 to the negative 4 moles, and divided by 1 liter. Okay, so we'll do this. The molarity of Bi2S3 solubility. I better call it the solubility, not really the molarity, but the solubility of that will be 2.00 10 to the negative 4 divided by 1 liter. Now, if it had been 2 liters, you put 2 there. If it had been milliliter, I got to change milliliter into liter, then divide it. Okay, I think you got the idea about that. So it's 2 times 10 to the negative 4. Now, what I'm going to do is I'm going to take that. I used the number from letter B, not C. But oh well, don't worry. I told you C. Let this be the new C problem. Okay, just forget what's written on C and do this instead. This many grams will dissolve in 1 liter to make a saturated solution. Calculate the Ksp. Okay, so first you have to find out what the solubility is. Now, I know this, so I know that's minus 2.00 10 to the negative 4. That's a solid. That much breaks off, and that's a solid. Now, if you're more comfortable with keeping the x there, you can say that is the x, and that'll be plus 2x. Oh, yeah, we better do that. Yeah, we better. Never mind. Minus x. These are both 0. That's plus 2x. That's plus 3x. And then so you get 2x there and 3x there. Now, so what you're going to have to do at equilibrium, you got to find out what is the bismuth plus 3 molarity, what is the S negative 2 molarity. So it'll be 2 times 10 to the negative 4 times 2 for that one. 2 times, so that's going to be easy, 2 times 2, 4 times 10 to the negative 4. And what will the 3x be? 3 times that. Actually, it's good that I picked this other number, because the math would be easier. Of course, the value we'll get will be different than what it would have been, but oh well. 6 times 10 to the negative 4. Okay, so the molarity of bismuth is 4 times 10 to the negative 4. The molarity of sulfide is 6 times 10 to the negative 4. Now, to find the Ksp, I'm going to have to erase this because my chalkboard is not big enough here, my video screen, whatever. Ksp will equal, we did this in the other part, right? Bismuth ion squared times the sulfide ion cubed. So bismuth is going to be 4 times 10 to the negative 4 squared times 6 times 10 to the negative 4 cubed. You're going to get a small number for sure. 4 10 to the negative 4 squared, 1.6 10 to the negative 7, actually 1.60. And that's going to be 6 times 10 to the negative 4 is going to be 2.16 10 to the negative 10. Some of these problems, the numbers can be so big, or so small that they might not even fit on your calculator, but if that ever happens, don't worry, we'll just see. So it looks like it's 3.46 times 10 to the negative 17. That's a very, very, very small number. And when you see a really small Ksp, that also tells you that not very much of that will dissolve in water. I mean, I erased, well, here it is. If only 2 times 10 to the negative 4 is x, that means 0.0002 moles of this dissolve in a liter. That is really, really small amount of material, okay? But anyway, do I need to? Yeah, I definitely need to do the last one, D, and then that will be it. But I'll have to, you know what? I think I can do it. I think I can squeeze it in right here real quick. Uh-oh. Let's just finish this up. All right, so here's what happens. It says we have copper iodate. This is mainly just going to be an algebra problem. Copper 2 iodate. So here's what you get. Copper plus 2 and IO3. It has to be negative 1 because there's 2 of them. Okay, even if you haven't seen iodate, IO3. There's 2 of them. All right, so they don't give you any molarity or anything. You don't have to have that because, you know, that's minus x plus 2x. Solid. Like I said, always write the icebox, even if you later decide to abandon it. Then it says the Ksp is 1 times 10 to the negative 15. They give you the Ksp. Wait a minute. Calculate the Ksp. Okay, yeah, that makes sense. I'm making sure I'm changing it up. They give you the Ksp and they want you to find the solubility. So what you do, you could actually find a lot of things from this. The Ksp value, write the expression, and remember they always give you points just to write the expression too. If you want to put a 1 there, just remember that's 1 copper and 2. Okay? Now the value of Ksp they give you is 1 times 10 to the negative 15 equals, and be very careful when you plug these in, copper at equilibrium, copper is x. And it's going to be just to the first power. No big deal. But iodate is going to be 2x molarity. But also, it has to be squared. This is why people can mess up on a Ksp problem. Because they skip it. Oh, it's easy, it's easy. But remember, you don't have anything on the bottom. Remember, solids never go on the bottom in a Ksp. They're never part of a K expression anyway. So you only have these 2. And people think, oh, it's easy. You can't forget. If you forget about that 2 affects the 2x, and it affects it being squared. So anyway, 1.0, 10 to the negative 15 equals x, 4x squared, x times 4x squared, which equals 4x cubed, right? Then you got to do the algebra. So divide, this is going to be a small number, I believe, too. Divide it by 4. 1 times 10 to the negative 15 divided by 4, 2.5 10 to the negative 16. Then you got to get the cube root. Actually, I better just write that down. 2.5 10 to the negative 16 equals x cubed. Now, to get the cube root, the easy way to do that is, remember, you raise something to the 1/3 power. 1 divided by 3 is 0.3333. So I could just say this number on my calculator to the 0.3333 power, whatever, is going to be x. That is the cube root, in case you don't have that on your calculator. Because if it were the 5th root, if it were x to the 5th power, then you would take like 1 divided by 5, which is 0.2, right? And you'd raise it to the 0.2 power. So I'm just telling you, square root is easy, but they sometimes throw in the cubes. So, and you might not have that on your calculator. So I'll just put 2.5 10 to the negative 16. Then I use the x to the y button here. And I'm going to raise it to the 0.333333 power. And I get 6.30 10 to the negative 6. Actually, just 6.3 10 to the negative 6. So 6.3 times 10 to the negative 6 equals x. What did we just find? We found x, the solubility. So let's label that 6.3 10 to the negative 6 moles of copper iodate, copper 2 iodate per liter is the solubility. That is the answer. 6.3, 10 to the negative 6 is the solubility of that one. Now, here's what they could also ask you, but they didn't do it on this question. They could say, well, what's going to be the molarity of copper plus 2 in the saturated solution? And it's just going to be X. So it's also going to be 6.3, 10 to the negative 6 molar. What's the molarity of iodate in the saturated solution? If they ask you that, it's 2 times X, 2 times 6.3, 10 to the negative 6, which is, oh no, I erased it on my calculator, 1.3, 10 to the negative 5 molar. Okay, so I'll just check it on my math. I'll double check it real quick here. 10 to the negative 15 divided by 4. XY 0.3333. 6.30, 10 to the negative 6. Yes, times 2 is 1.3, 10 to the negative 5. Yes, everything is good. Okay, so I did more than you had to there. All right, you should definitely be able to do those problems that I assigned for you. And we only have one more section left, I believe, in this chapter. And it is on what's called precipitation. And that'll be next time. So, see you.